like today. And I've been told to remind you that you can log into the Bornhack site, go to the program, and then read feedback from the speaker. And please do that. So then, welcome, Simon.
Thank you. Right, so yes, my name is Simon Schein, and I work with cryptocurrencies for a job, and I've been doing that for half a year. But I have had an interest, like so many of us, ever since about 4 years ago, I think. And back then I was helping a friend with his bachelor's project, which was a compiler for a blockchain language. So this was a bit before it got very popular, but still Ethereum was sort of mainstream lingo among computer programmers, I think. So back then I only really had an interest in compilers and programming languages, and to some extent that's still my main motivation for doing any of this. The purpose of this talk is to kind of give an overview. I tried to go as far as I could, but of course there's like an event horizon of new inventions. But this is kind of like a picture of how some of the programming languages, smart contract languages look like today. What are their constraints? What are the virtual machines that they run on? What's the design space? And I would like for the overview to go into a kind of a discussion about what's useful and what's missing. Unfortunately, and yes, please do give me feedback. I didn't complete my slides entirely. This is the first talk I've given. So I think I underestimated the amount of effort that goes into a presentation. So let's see how much I can supplement with hand waving. So my motivation is, as I said, I want to show a few examples because this kind of gives a picture of what we are up against. I would like to continue discussion. And to my knowledge, there is only one place on the internet where there is any kind of active discussion on language development for blockchain, and that's this Gitter EVM lang design. There's a few people in there, mostly hobbyists. I think not a lot of people get paid to do this, but that doesn't really have to be the motivation. This is kind of like an overview of the languages that I'm considering. I don't have examples of everything, but I'll just be mentioning them because they kind of, there's lots of other languages. And I'll just kind of outline why I chose some and chose to disregard others. But also there's kind of like a timeline also, because obviously Bitcoin was invented more than 10 years ago, and the smart contract language they have is less sophisticated than what we see today. So that's also a factor here. So I thought it would be fun to just kind of outline, because you don't really hear about smart contracts in Bitcoin. It's not really a thing. It was designed to be a possibility, but then in reality, it's not really happening. And there's a reason. So just to be clear, the first design attempt at a smart contract language was the scripting language that powers the Bitcoin transactions. So whenever you make a Bitcoin transactions, that's actually a tiny contract that basically just says, transfer this money to this address. And there's some public key cryptography that has to work out for that transaction to actually come through, for the contract to succeed rather than fail. But other than that, it's really just one instruction of transfer money. Then of course, with Bitcoin, such a contract language, so what they did originally was create a small virtual machine and make it stack-based. And in Bitcoin's script language, there's no concept of recursion. There's no concept of kind of going back and doing the same thing over and over, no loops, it's just straight line code. That's one very obvious way to limit how much transaction is allowed to do. But it also comes at the cost of, there's also a limited amount of things that you can express. the only examples of applications that I've been able to gather, and feel free to add to this, is things like, for example, if you have a transaction and you want multiple senders or multiple signatories. So for example, you could have an escrow service. This is one of the examples of Bitcoin applications that people like to say. So for example, you might send money from A to B, but C, even though they don't have any money or access to any funds, they have to kind of provide their signature as well. That's an option you can have. And that of course works for a lot of handling disagreements about trades and so on. So it's not an insignificant application at all. And of course, what Bitcoin enthusiasts also kind of highlight as a feature of the scripting capability of Bitcoin is you can do micropayment side channels. So you can have things that are next to the blockchain that get kind of executed in some kind of other environment. And then whenever you want to finalize the transaction, you kind of propagate it back into the main blockchain. And so this is kind of in the case of Bitcoin, it often requires elaborate engineering to make any of this work, because the primitives aren't really a part of the core scripting language. It's kind of dependent upon a lot of other stuff being made. So you can do it in somewhat safe manners, but it requires a bit more work. Also, another example is CoinJoin, which is a way to kind of try to anonymize Bitcoin transactions by shuffling around inputs and outputs. Again, maybe the usefulness is limited, but these are some of the examples of the things that you still see Bitcoin companies want to try to do. An interesting observation was that in 2010 there was a security vulnerability in the Bitcoin node. It's written in C++, and the left shift operator in this script language expressed undefined behavior. So basically what they went and did was they disabled a bunch of very primitive operations, such as multiplication. You can't do multiplication on the Bitcoin script language. So you might think that's maybe a bit limiting. Maybe you want to multiply things at some point if you're dealing with money, I guess. But apparently that's not really the most intrinsic operator. If what you mostly do is just transfer money around, and people do the multiplications offline or off-chain. So this is kind of where Bitcoin stopped being scriptable, was when they kind of disabled almost all of the mainly useful scripting. But then, of course, Ethereum came around and provided a much more ergonomic interface. They created domain-specific languages for high-level scripting, so it wasn't just assembly. There's no scripting language in Bitcoin that is usable. You have to kind of manually construct transactions in binary data that expresses the script language bytecode. So there's nobody writes script by hand, or you have to write it by hand, so nobody really writes it. But with Ethereum, they decided we should have many languages, we should have many implementations of our nodes. They created this ecosystem, and they wanted to kind of have like some equilibria in the ecosystem, so you don't end up with the same kind of social problems that Bitcoin has. Now, it's still to be seen if that's a success or not, but from a language perspective, this gave birth to a bunch of high-level languages, and I would say today only Solidity really survives. If you go to the forums, or if you go like Google around what are my alternatives, what you often see, for example, there was a Lisp-like syntax called LLL, and there was a Python-inspired called Viper, and Solidity is kind of reminds of an object-oriented language, except you don't have classes, you have contracts, but you have inheritance of contracts, and you you have extension methods, and you have operator overloading, and there's a whole thing, a lot of language features that resemble class-based object-oriented languages. The EVM itself is quite interesting. I don't have a lot of experience with Solidity myself. I only scripted Solidity for about a month, and the rest of the time I spent writing compilers that target EVM directly. EVM is a very simple abstract virtual machine, so it has like a stack, just like most other cryptocurrency virtual machines like Bitcoin and some of the others that I will mention. It has like memory, so you can do arbitrary indexing into memory and say I like the ith, like the 24th word. And it has persistent storage, so if you have a contract on chain and you contact it, it can remember things between calls. Then you can contact it tomorrow and it will have remembered whatever was changed in the contract the day before. So of course, this is necessary for having persistent contracts that evolve their execution over time. Another interesting property of EVM is that all the arithmetic operators overflow. So if you have two very big numbers and you add them or you multiply them or you take the power of something, if the result is bigger than 256 bits, which is the standard word size on the architecture, you simply just get a wraparound and you're not informed. So it's very easy to end up with these arithmetic bugs. You're not informed there was a bug. You just get a very big number when you expected a small one, or you get a very small one when you expect a big one. Or ideally, for something as critical as financial transactions, you would at least expect maybe an error. Like, I tried to multiply the numbers, what ended up was bigger than I was able to express, so I'm gonna throw up and die rather than silently agree. But this is the state of the world. We have these overflowing arithmetic operators on the most popular scriptable blockchain. And what you can do instead is kind of use libraries that add safety on top. And as an example, the cost of doing this after the fact is that normally if you want to add two numbers, it costs 3 gas, whatever gas is. And wanting to use the safe math library for the same operation is like some factor higher, about factor 10. And you could say the same thing for a bunch of other operators. Really, in practice, there is no other choice right now than to use Solidity and use the safe math library and employ a bunch of very critical design principles to avoid some of the most typical bugs that occur as a consequence of the language being the way it is. I would also like to add that Solidity is actually in active development. It was about 2 weeks ago that the most recent major version was released, and I don't know what you call this, like a minor version release, but it was a gradual improvement. They remain backwards compatible. So they treat it like a serious project, but they also add new paradigms. Like, we realized that maybe the things we recommended you in 0.5, they're not really so safe, so maybe you should do this other thing. And then they try to patch things up by adding more rules to the linter. And that way Solidity remains backwards compatible, but still new bugs occur, and then the language kind of evolves like that. This is very ergonomic if you come from maybe a JavaScript background, or I don't know, Java or Go, or some kind of high-level imperative language. And that's the state of the art. I just have one honorable mention, which is Viper. It was one of the competitors for Solidity that never really got popular, but they are still active in development. It just seems more like a hobby project at this point. So there's no real money invested in Viper. Here's an example of a Solidity program. This is a power function. This is kind of geeky in a way. I had this project where I needed to take the power of something, and the standard library does not have a power function. It does have a power function, but the power function overflows. And as you know, with powers, they tend to grow quite easily. So having a power function that doesn't tell you when it overflows is kind of a problem. So this is a way to create a safe power function. Unfortunately, SafeMath didn't have it, so you had to extend the standard library. Now, of course, you might wonder what's an efficient way to do a power function. And this is just an attempt to do so using like a logarithmic amount of multiplications. This is standard algorithm for doing efficient power functions. But also there's some funny stuff going on with normally on an architecture where you have arithmetic operators, you might expect that, for example, a multiplication is some order of magnitudes more expensive than an addition, and a power function is some order of magnitudes more expensive than a multiplication. But on Ethereum, the cost model is entirely defined by some arbitrary amount of gas that you spend on these operations. So that's what you actually have to take into account when you think about what's the least amount of resources I spent on doing some kind of computation. You just look up in the table in the Ethereum yellow paper, how much does this operation cost? And then you can kind of do a cost benefit analysis and realize that maybe this is the best way. So the alternative, for example, for the safe math versions of multiplication and addition is you do the operation and then you check afterwards, did I overflow by checking is the result bigger or smaller than something? And the question is that possible for doing power exponentiation? And my answer so far is I haven't come up with one, but this is kind of like the de facto standard. So this function is, you can find this in several places. Another honorable mention in terms of the design space of in specific Ethereum and EVM related compilers is a small language called Formality. It technically isn't necessarily just a blockchain language, but the author behind this language, this is a proofing language, so it's not technically just a programming language, although you can program in it, but you can also prove things. And so the author is one of those computer science people who like proving things rather than executing things. And he, as a PR stunt, or because he's interested in blockchain, he it's a guy called Victor Meyer. He created this, compiler for a part of Formality, where he can execute beta reductions on the blockchain in 200 gas. And this is kind of like his claim to fame with this compiler. I will try to decompact this for people who don't have an interest in functional programming. It basically means that the primitive, like evaluating a function 1 degree, costs approximately the same as loading something from persistent memory, which is not the cheapest. So as I mentioned earlier, like a safe addition costs 28 gas, and a beta reduction costs 200. So it's still a bit more expensive than doing the most primitive arithmetic, but it's comparing this to making a contract call another contract or perform a transaction of something, that's still several orders more expensive, right? So this is kind of his attempt to say that we can quite simply have provable functional code on the blockchain at a reasonable cost using current technology. And I think that's worth mentioning, even though this is very researchy. This is an example of a proof that you can execute on the Ethereum blockchain. And I won't go too much into details. Next, I'm going to, so maybe I should go a few slides back and say that the blockchains that I'm looking at, because of course there was Bitcoin and Ethereum, these are kind of like what you would call first and second generation blockchains. And then you have all the companies now that are trying to kind of get a part of the pie and try and advance some of the research related problems that occurred in the first blockchains. And of these, I've kind of mentioned 3, although I didn't really get time to go into EOS. It's not really on my radar as much as the other 2. But in particular, Tezos and Cardano will be the last subjects of this talk, kind of looking at what the languages that are designed for these blockchains, what they have to offer, and also what are the implications of how the blockchains, like what are the primitives, like what features do the blockchains offer, and how does that affect language design? Because what I will want to try and conclude eventually is that some of these languages, of course, have very cool features, but what if there was a time when we programmed to one particular architecture, and then eventually we tried to kind of standardize the languages across architectures. And the question comes, will such a thing happen for blockchains? We are still quite early on. We have only seen the first 5 serious architectures, and the languages across them aren't really common. Nobody made a cross blockchain platform language as such. And the question is, what can we even expect from such a language? But before I get to any concrete conclusions about this question, let me just iterate through a few of the 3rd generation blockchain languages. So Tezos is one project. I don't recall exactly how old it is, but they've been going at it for a while. They wrote most of their software in OCaml, a functional language, and one of the cool features about, I would say Tezos has 2 cool features. One is that they're a stack language, so the most primitive assembler language of the blockchain is type safe, so it has a type system. So normally if you go and write assembly programming, that is when you disable all type safety, right? Normally when you write C, you have types, and then when you compile it to assembly, it's just words and addresses. And at this point, because we are working with an abstract virtual machine, we can really define a type system for it, and it doesn't really matter that it is expensive, because we won't be carrying out a lot of computation on it compared to what we use on a regular CPU. The other feature, besides the assembly language being type safe, which still remains to prove that it was really worth the effort, but at least it's a feature that means that they can catch some bugs during compilation. For example, if you want to add 2 numbers, but the stack is too shallow, you cannot do that. And I guess you can create more complicated examples of when the type system will also benefit you. The other thing is a self-amending protocol, and this is really kind of what 3rd generation blockchains are trying to fix in regular blockchains, which is, for example, if someone thinks, hey, maybe the blocks should be able to contain more transactions in Bitcoin, you have a hard fork where you kind of create an economic competition between people, like what fork do we vote on, and that's incredibly expensive. So is it possible to make forking a part of the protocol? So whenever we have a disagreement about how the blockchain should behave, can we make those disagreements expressible on the blockchains as kind of programs? Because if we can, then the cost of determining the outcome of such a, let's call it vote, will be considerably cheaper, and it won't involve a lot of people moving to and from different versions and forking software projects and so on. So that's really the big goal for these new blockchains, at least from my perspective. So I mentioned 3 languages: Microson, which is the assembly language. It's worth mentioning, just like EVM is, because some people might like to actually write stuff directly in assembly, even just for the purpose of creating new compilers. Then there's Liquidity and Lego, and there's a few others, but Liquidity is based on OCaml itself, because the whole ecosystem around Tezos is based on OCaml. So they created a contract language that also resembles this style of programming. And I think this is maybe a bit hard to read example, but the point is that a part of the contract's persistent state, the storage part, the kind of the hard disk of the contract, is expressible as a type. So you can kind of say, rather than for example, in Solidity, where you might have the first part of a contract saying, well, we have a private field and it's an address, and then we have another private, and it's called owner, and we have another private field that is an array of addresses, and then we have a private dictionary mapping something to something else. And this is kind of like the mutable state of the contract. And every time a contract method is called, it changes that state. So instead, with liquidity, you have you start by typing your state. You say what is the type of my state, and then you go about in defining the methods that transform the state. You do that using pattern matching, and you have algebraic data types. So this is very much like how a functional programmer would design a contract language. I think liquidity is a good example of exactly how you would do it using classical functional programming. Then I have Lego. I didn't provide an example of Lego just because I ran short of time preparing, but I would say that Lego is kind of like inspired by Go, thus the name, which is yet another example of what. So this behavior of having liquidity resembling OCaml and Lego resembling Go, this is kind of copying the behavior of how blockchain languages were formed on Ethereum. It's like we try to cater to the what do our potential customers, language customers like? Well, some people like JavaScript, and some people like Go. We'll just make the syntax look like that, and maybe they will come and program. Whether that strategy is good or not, at least this is what is currently being. That's the approach that the Tezos community is going into, and I think liquidity or Lego, they are somewhat equally mature. The Tezos blockchain itself is not as mature as Ethereum yet at all, so you don't see a whole lot of applications, but I know of people who are getting paid to write in these languages, so it's not that it's completely non-existent yet, unlike, for example, some of the languages like Viper. I don't think anyone uses that commercially. So the last one is in my list of languages is Plutus, which is Cardano's take on how to create a blockchain language. And the one that I didn't get around to explaining, I also didn't embed an example of Plutus, but I will explain in depth because this is so far my favorite. It works much the same as EOS, except for their choice of native language. So Plutus does this thing where instead of saying we have a dedicated scripting language and it's called Solidity and this is the syntax and you have a compiler and it compiles to this bytecode and then you push it on the chain. What they say instead is a contract, you write that using a normal programming language. In case of Cardano, it's Haskell. But in case of EOS, it's C++. So basically, you express a contract by inheriting from some class or from by using some library that has these basic primitives. So this is like an embedded domain-specific language rather than a full-fledged domain-specific language. So the syntax is Haskell syntax in case of Cardano and Plutus, and the program, the contract itself, is a Haskell program. And when you combine that Haskell program, parts of that Haskell program is expressed using template Haskell. And template Haskell is this part just like C++ templates that gets compiled during, that gets translated into something during compilation. So what you can do is you can have like some kind of a sophisticated type check and say, is this actually a reasonable contract? Does it do what we expect contracts to do? Part of this is safeguarded by the type system of its native language, Haskell or C++, and part of it is safeguarded by some kind of translation step in the template part of the language. So the output of a Plutus program as you translate it is twofold. One part is bytecode that gets injected into the blockchain, and another part is kind of a library or wrapper program that let you interface with the blockchain. And when I learned about this, the first thing I thought about was ASP.NET and web forms. I don't know if any of you did Microsoft website programming in the 90s or in the early zeros. This was a horrible experience. Most of you probably remember if you go to a website and you decide to click back, and the website says, wait, before you do that, are you sure you want that? Because I was actually in the middle of posting to a form, and if you go back, you lose kind of this implicit state that I'm in the process of doing. And that kind of unfortunate side effect was caused by the ASP.NET Web Forms framework generating some kind of, they kind of abused HTTP post messages so that they could accumulate state in their kind of web application. So it wasn't really a website, it was more like using HTML4 as a GUI toolkit, somehow something like that. And most people who had experience with this kind of disliked it, but I thought there was actually one part of this that was really beautiful. And I've seen this in other more modern web frameworks, and that is they have one piece of code, in their case it was C#, I think. And that piece of C# code, part of it translated to the backend, and part of it translated into JavaScript front-end code that interfaced with the backend. So you only had like, you kind of generate the front end and the back end, and they work in synchronicity. And this is kind of what I see the third generation blockchain infrastructure doing all over, in Cardano's and EOS's case at least. They say, we're not going to force people to learn a new language. That's kind of like Kool-Aid. We just want people to use the regular languages that we decided was mature enough infrastructure code, like Haskell, C++, OCaml. These kind of renowned for being sophisticated kind of languages. And then we just make libraries. And those libraries express the contracts. And besides wanting to create just the contract code, you also want to interface with it, and you get those at the same time. So this is kind of like state of the art in terms of the infrastructure surrounding the languages. And I think I'm about to reach my final slide, and the only thing I got to conclude on was that some of the features in the newer blockchains that seem hard to create a common interface for is the self-amending protocols. Because in, for example, Tezos and Cardano's case, if we imagine that both of these invent some kind of thing that they want to be voting about. For example, some of the things you can vote about right now is changing the initial parameters for how to redistribute the wealth that is generated as an inflationary function of the blockchain. So every time a block is mined or baked or whatever people use to as a metaphor, some cryptocurrency is given, and how is this distributed among the miners or bakers or whatever. This is the parameters for this distribution is one thing that is currently very obvious that you want to be able to vote about. But maybe the specific ways that you do this varies from blockchain to blockchain, and maybe the particular things, if you have a completely self-amending, like we want a new instruction and it has these semantics kind of thing where it becomes purely kind of a liquid state of like what's the blockchain? Well, it is whatever it thinks it is right now or something. How do you create a language that targets a machine architecture like that? Is probably not a good question to answer. But then what is the least common denominator at least? Like what seems reasonable to do on all blockchains? And I didn't write a slide for this, so I'm gonna end the slideshow here, but I do have one answer. It's not the quest for a new general purpose programming language. It's actually returning to the pet project that I've previously worked on, which is this language called Lyra. At this point, it used to be called Dagger at another point. I suppose both names are equally valid. And what it does is it lets you express derivatives. So if you are into stock trading, you have all these swaps and futures and whatnot. And this is a very simple language that only lets you talk about stakeholders, conditions, timelines, but not really state of a contract that is all implicit to this language. So this is kind of a way to create a high-level language that really only cares about, let's say there is a stakeholder, and then let the runtime of the system figure out how do you become one. That's not really the language. Whereas, for example, in Solidity, you say, well, a stakeholder is someone who calls this function on me, and once that is called, I make a record of that person being an entity in this contract, and now that person can make other contract calls that opens or trades positions in some kind of market or whatever, or has the voting rights to move funds somewhere. And all of the mechanics of exactly how it is executed is left as an implementation detail. So this, I think, is at least an example. So I had, it's at least an example of a declarative, very high-level language. It doesn't let you do a whole lot of things, but the things it lets you do, you can actually implement in multiple ways, and it's quite blockchain agnostic. Another interesting question is, well, besides Lyra, what other angles are there to express smart contracts, whatever they may be, on multiple blockchains in ways that don't conflict with the very particular natures of the individual blockchains. And I think this concludes at least what I have to say so far about blockchains, and I would like to offer to discuss if anyone has a take on the language design space, or if anyone has a favorite language they think has a better potential than others. And yes, thank you for listening. So, any questions?
So I haven't written software for the blockchain yet, and there's one thing that I'm still very unclear about, and that is, when do the programs actually get executed? So do you just publish a program on the blockchain and then it's immediately executed by all nodes of the blockchain network? Or can you also define triggers, like if a certain stock falls under a certain level, then execute this contract? How are these programs running?
Okay, I'm just going to repeat the question. I'm not sure exactly how the speakers work, so I'm going to repeat it. So the question summarized is, how exactly are blockchain contract programs run? When are they run? Is it when you upload them to the chain, or can you refer back to them later? Or can you have some kind of event model, or is there, how do you actually execute it? And I think it's a great question. I could maybe say that in terms of Ethereum, both because that's what I have the most experience with, and also because I think it is quite generally the way to do it. So future blockchains might do different things, but this is like the standard model right now. And that is, so you have a bunch of EVM bytecodes. You kind of compile your Solidity program or whatever, your Lyra program, whatever. You compile it into bytecode, and you want to upload it to the blockchain. So you publish this to one of the nodes in the network, you pay the fee, and the fee depends on how big the program is. And then when it's time to kind of build the block, the nodes, in order to build a block that contains your program, they execute your program. And of course, update the state of the total blockchain. In this case, your program is actually just a script that runs, but typically if you want a contract that has a persistent state, the first thing a contract that you upload wants to do is copy a part of its own memory into the blockchain. So this is in Ethereum's case, it's an instruction in the data set that says all the stuff I just uploaded, copy some of that into the blockchain. Once you have done that and paid the price for that, it exists as an entity, it has an address, and you can contact that address if you want to further communicate with the contract. Then in later blocks, at some point in the future, you can, because you was told here's your address for your contract, you can refer to that contract. And whatever logic you put into that address space, it will kind of trigger. So you can have methods, for example. You can have like, my contract has like a put funds into me kind of method. And then you might call that function. And as a precondition to calling that function, you might supply some currency. And then the contract will deal with whatever logic it does. For example, it might store that currency in its own wallet, or it might contract another contract. So that's mostly how you do that. You can, the moment you upload a contract, you actually execute it, but part of that execution is copying its own program into the blockchain in kind of a persistent way. And the other thing is, when you call contracts in later phases, you can also emit events. So there's an opcode in Ethereum called a log. So you can log an event, something happened, and depending on what the identifier for that log message was, you know, by observing the blockchain off-chain, you have maybe like a listener that just a blockchain node that just looks over, like you have maybe a JavaScript or a Go or a Java program that just says, until this event is triggered, this happens off-chain, then do something. So all your event listeners are off-chain. It's not possible to have like a triggered event on-chain. This is kind of confusing, I think, to most people, but it works out. So for example, you might have some kind of a pool of some kind of currency or asset. Let's see if that works. And you might say, well, if that goes below some amount, people should know. And then the moment people should know, maybe you can kind of put more something into this contract at a cost or a price. Maybe you get a benefit for doing something that is needed. And that trigger is kind of, that event is emitted to everyone who cares to listen to it. And then they make sure to make an on-chain call that addresses the contract in its current state. So that's how you execute, through initial deployment and calling into contracts and receiving events being emitted off-chain and then reacting back by calling on-chain events. But of course, this is also related to the current model. So a part of this is necessitated by, for example, EVM having these log messages, and you can't say for a contract, please listen to this other contract. And asking something to listen has to happen off-chain. That's a restriction in EVM. It's not necessarily a restriction for all blockchains. And also the fact that you kind of make these calls based on events being listened to, that's also one model of computation. You could also do this using more, there's a lot of, the Cardano project, for example, has a lot of the underlying theory behind this blockchain relies on I think it's phi calculus or something like that. So it's an extension to the pi calculus, which is a process calculus. So they want to kind of like create a formal definition for how the chains kind of diverge and merge, and how asynchronous processes can update kind of a global state and stuff. So there's a lot of theory that goes into that. So any kind of computational model you can build on top of the theory of a blockchain actually gives you more like a bigger, so for example, you might like to create a blockchain language that is more based on the actor model. And the actor model is hugely popular today because you have a lot of processes, and a lot of mainstream languages today offer you very cheap multiprocessing, right, through green threads. And so this is something like a Go programmer might really enjoy, because they're really proud of the, what are they called, the channels, Go channels. Or an Erlang programmer might think that their processes are really inexpensive, and so this, like, you could have a blockchain language with a mailbox type of processing events, right? There's nothing really preventing us from doing that, but we don't see it yet. So this is kind of the design space I think is bound to be explored, but also maybe could be fun to explore. Any other notes or questions or comments?
Could be fun to do a workshop.
Yes, it could be fun. I think in terms of doing a workshop on blockchain stuff, a point of start would probably to even get a contract on chain. So I think doing like a Solidity workshop or an EVM workshop, or depending on what people like. I'm more into compilers. I don't really care that much about doing particular contracts because I don't really know what to use them for. But another fun thing is so my boss at my full-time job, he has a summer course these weeks, and one of the things is students there have to deliver a project, and this project has to kind of have some hypothetical application value. So it's like a distributed application. And an example for such a distributed application could, for example, be like an insurance fund. How do you make a blockchain insurance fund? Why would you make one is another good question. But you could also say, how do you put shared funds if you have something like a union or a collective of people who have shared funds and they want to make sure that it's kind of like the bookkeeping is being registered completely transparently, right? Then a blockchain might be a use case for that as well. Mostly because it's fun, not really because it's necessary. But at least this kind of application development is also a good use case for a workshop because you can get started quite quickly.
Would anyone be interested in getting started with hacking on blockchain stuff?
Yeah. I mean, I'm going to sit and do something very similar later today anyway, so we can call it a workshop if we get a good amount of tables and chairs. Yeah, I'm not sure.
There's one final question from YouTube.
Yes?
Does the blockchain scale?
I'm pretty sure this is Torkild, but he was trolling me on Stack Overflow recently, so I don't know Torkild. Yes, I have maybe one final note because I still have plenty of time. So one of the things in terms of programming languages contract languages that I find very interesting in my brain that I can't let go of right now is, so there's this language, Lira or Dagger, that is very high level. It only lets you express financial derivatives, but it doesn't really tell you, it doesn't really tell the programmer how to settle this contract between people. We have a working compiler, Torkild initiated this work and did most of the job in that, but it works on a very basic assumption that before you can initiate a contract, you need full reserves of every all value transfer that could happen during the lifetime of the contract must be paid up front. So we make a big pile of everything that we could possibly move around, and then during the execution we move it around, and then through a bit of ingenuity, sometimes we can conclude that, well, maybe this person can get a refund because not all of the funds are going to be used at this. From this point, we know that we have excess funds, so we just give people money back. But this is kind of like a full reserve model of executing a derivative. Often, if we try to look at the real world and we see, for example, maybe you see a contract where one party is allowed to buy oil from another party at some certain price for this duration of time unless some condition, you usually don't assume that they will, before they buy any oil, they just put down the money for the maximum possible oil they could buy. That might be trillions of dollars. So this type of contract is completely useless for real world applications where people actually want complicated derivatives. So what you want is kind of like a way to settle this contract without having a full reserve. This is kind of like I guess you could call a research problem within this very narrow scope of language design. And I have an idea for it, or a few ideas for it, but finding time to look into this is kind of scarce for me. But if anyone is interested in that, I could talk a lot about that. And I won't bore you with the details because it rests on a few assumptions. All right, I think that's it. Thank you.